Molecular shape and polarity. So we've talked about polar bonds. If you have a diatomic molecule, just two atoms, there's only one bond. If the bond is polar, the molecule is polar. And this comes about because the chlorine is more electronegative. It pulls the electrons over towards itself. And so if we look at electron density, we see that there's more electron density on this end of the molecule than on this end. This end will have a slight negative charge, and this will have a slight positive charge. And that affects the properties of that substance. In a polyatomic molecule, it's a little more complicated. It will depend on the geometry. So you can have polar bonds and have a nonpolar molecule. If you have all nonpolar bonds, though, the molecule will be nonpolar. In order for a molecule to be polar, it has to have at least one polar bond. So let's look at a couple of examples. Let's look at carbon dioxide. So here we have the molecular shape for carbon dioxide. It's linear. Each of these bonds is polar. The oxygen is more electronegative, so it's pulling electron density to this side, and this oxygen is pulling electron density to that side. So you could think about these polar bonds as maybe people playing tug of war, right? So here's the middle. Maybe you've got one guy standing in here, and oxygen's pulling on this side, and oxygen's pulling exactly on the other side. Is anything going to move? No. Now maybe carbon's arms are going to fall off, or he'll lose his grip or something, but these two oxygens are equally strong, and so the forces are just actually opposing each other. Dipole moments are vector quantities. Do you remember what vectors are? Vectors have a direction and a magnitude. We represent the magnitude as how long the arrow is, and the direction as the direction it's pointing in. So we could interpret these arrows as being vectors. Yeah.
So even though it has two polar bonds, the molecule is nonpolar.
Yes, because the bonds cancel out. So if we look at the electron density, it's a little bit lower in the middle and higher on each end, but there's not a positive end and a negative end of the molecule.
Okay, so you can say that in order for a molecule to be polar, it has to have an odd number of polar bonds?
It's not necessarily an odd number. It's more the arrangement, and I think your questions will get answered in the next couple slides. So if we look at water also has two polar bonds. But water's shape is this bent structure because there are two lone pairs on the oxygen, and so that forces these hydrogens closer together. Water is not a linear molecule. So here we have a dipole moment pointing towards oxygen and another one pointing towards oxygen. And so you can imagine that oxygen maybe is the dad, and the hydrogens are his twin boys. And one's pulling in that direction and one's pulling in this direction, but dad's stronger and he's just backing up and dragging those two little boys, right? These are not in opposing directions. The opposing directions is a bit like a number line. So, you've got 0, 1, and 2, and then you've got -1 and -2. For the carbon dioxide, you've got one vector, one dipole moment going in the negative direction, and one of equal magnitude going in the positive direction. And so it's the same as 2 plus -2. It adds up to 0. Here, we're not adding in a linear form, and so it doesn't add up to 0. So there's a net dipole moment. We'll go over in just a minute how you would add those two vectors, but the net dipole moment points straight up through the oxygen. If we look at the charge distribution, the oxygen end is a little negative, and the hydrogen end is a little bit positive. So one end of the molecule is positive, one end is negative, and that's what a polar molecule has. So we draw the Lewis structure, we determine the molecular geometry for that molecule, we identify if there are polar bonds in the molecule, and then we'll represent those as vectors that are pointing towards the more electronegative atom. The length would be proportional to the difference in electronegativity. So you can see this could get pretty complicated, right? You could have two polar bonds that are directly opposing each other, but if one is with fluorine and one is with oxygen, the magnitude isn't going to be the same. And so even though they're in opposite directions, they're not going to add up to zero. So the rigorous way is we determine if the polar bonds are going to add together to form a net dipole moment. If they sum to zero, it's nonpolar. If there's a net vector, then the molecule is polar. Well, how do you add vectors? Just going to go over this very quickly because you can do just fine in this class without knowing how to add vectors. But I'd like you to at least, wrap your brain around it a little bit. So in one dimension, things are easier. So one dimension, the vectors lie along the same line, and they're either pointing to the right or they're pointing to the left, positive or negative, just like a number line. So here we have a +5 vector and a +5 vector. We add those together, we get +10. Here we have a -5 and a +10. When you add those together, you get a net vector going to the right, +5. Here we have a -5 and a +5. They're in exactly opposite directions and equal in magnitude, and so they add up to 0. Does that make sense? In 2 or more dimensions, we can think about it this way. So here we have this vector A and vector B. And they are, at some angle slightly less than 90 degrees to each other. How do we add those? We draw a parallelogram. So we've got this vector B, and we're going to draw a line that's parallel with B, starting at the end of the A here. And then over on this side, this line is going to be parallel with the A. So we're just taking our two vectors as two sides of a parallelogram. We're going to complete the rest of it. The sum of these is going from this point of origin to the other corner of the parallelogram. Here's a different example. These are off in different directions now. But again, you draw a parallelogram, and the sum is from one corner to the other corner. If you have 3 or more vectors, what you do is you start with 2, you find the sum of the 2, and then you add the third one in. So a couple of examples here. We have A, B, and C. So we can add A and B together, and we get R. Then we can add R to C, and we get R prime. So it's not at all obvious, looking at those 3 blue vectors there, that their sum is straight to the right, but it is. Here in example 7, we also have 3 vectors, but they are all equal in length, equal in magnitude, and there's 3 of them, but they're pointing out from the same point, equally spaced, right? That's a triangle that they're forming. So if we take these 2 and add them, we get R. And then if we add R to C, that adds up to 0. This one is very symmetrical. The vectors that are being added are equally spaced around. This is 2-dimensional. Here the vectors were not equally spaced. There were different angles. The vectors are all the same length. Here the vectors were different lengths. So something very symmetrical like this, you can have polar bonds, but overall have the molecule be nonpolar. You can also imagine, playing tug of war, and you've got somebody standing in the middle, and there's somebody pulling on a rope this way and that way and this way. And if all of those forces are equal, they cancel each other out, right? and the guy's not going to move. Here's some situations with common molecule geometries where we can end up with polar or non-polar. That's all very nice. But here's my shortcut. So all of that was true, but here's a shortcut that works most of the time and is so much easier. So a molecule is nonpolar if both of these conditions are true. No lone pairs on the central atom. All the atoms that are bonded to that central atom are either the same element or they have the same electronegativity. When both of these factors are true, then all of the bonds around that central atom are evenly spaced and they're the same magnitude, and so all the vectors add up to 0. You throw a lone pair in there, it's probably going to be polar. So, molecule is nonpolar if there are no lone pairs on the central atom and all the atoms bonded to the central atom are the same or have the same electronegativity. So let's practice that. Determine if carbon tetrafluoride is polar. We still need the Lewis structure because we have to see, are there any lone pairs on the central atom? So I'm going to go through this quickly because the point of this is not learning how to draw Lewis structures. You can double check later, but it's got the correct number of electrons. All the elements have octets and they all have 0 formal charges. It's a good Lewis structure. We're going to look at this and first ask ourselves, are there any lone pairs on the central atom? No. So the first condition is met. There are no lone pairs on the central atom. Are all of the things bonded to the central atom the same? Yes, they are. So this is a nonpolar molecule. These 4 electron groups would arrange themselves in a tetrahedral shape where the 4 things are opposing, they're equally spaced away from each other. They're all the same length, and so their vectors add up to 0. If we stick something else in here, if, say, we put iodine in here, is it still nonpolar? No. They are still equally spaced because there's no lone pairs, but this iodine has a different electronegativity than the fluorines do, and so the magnitude of this vector is going to be different, and so they will add to a net vector, and that'll be polar. So you stick that in there and you've got a polar molecule. Is that easier than adding vectors? Yeah, and it works most of the time. The polarity of molecules is really important because it has a big effect on both physical properties and chemical properties. Water is a polar molecule, and so just like the North Pole and the South Pole of magnets are attracted to each other, the positive end and the negative end of 2 adjacent water molecules are attracted to each other. It's an electrical attraction, not a magnetic one, but it's similar. So here we have a picture of some marbles. The solid marbles are magnetic marbles, and these are ones that have swirls in them. Those are just regular glass marbles. The magnetic marbles are attracted to each other by magnetic forces. Those magnetic forces have no effect on the glass marbles. And so you can imagine what would happen as you dump all these marbles together. The magnetic marbles are going to clump together and they're going to push out the glass marbles, right? Because these are going to try to get close to each other, and those are in the way, and they're just going to kind of get scooted out. This is what polar molecules do. They're attracted to each other much more strongly than nonpolar molecules are attracted to each other or to the polar molecules. And so they will push out the nonpolar molecules. This is why oil and water do not mix. The oil molecules have a small attraction for each other. It's very small compared to the attraction that the water molecules have for each other. It's a little bit like a clique. You know, you've got this group of people, they are just really tight with each other, right? And here you are on the outside and you want to get in and participate in their stuff, but they're just so tight with each other, they have absolutely no time for you, right? And so you're just stuck here on the outside. The reason that the oil floats is because it's less dense. There are other substances that are nonpolar that are more dense than water, and they'll form a layer on the bottom with the water on the top. Any questions? So polar and nonpolar substances generally do not mix with each other. I think we all have enough life experience that we know if you get butter on your hands or Crisco or bacon fat, grease from working on a car, anything like that, you're not going to be able to get your hands clean by just rinsing them with water, right? That greasy stuff does not come off with water. You have to use soap. So I'm going to tell you how soap works. This is an illustration of a soap molecule. Most of it is this long chain of carbons and hydrogens. Carbon-hydrogen bonds have a small enough electronegativity difference that they are considered nonpolar. And I've told you should remember that. Carbon-hydrogen bonds are nonpolar. So all of these are nonpolar bonds, so this end of the molecule, which is most of it, is nonpolar. At this end, we have a couple of oxygen atoms. Those oxygen atoms are going to cause this end to be polar because they're going to pull electron density from the carbons that they're bonded to. So we've got a little bit of negative here. So this polar head of the soap molecule is attracted to the water molecules and is going to interact well with them. This nonpolar tail part will interact with the grease. So what happens is, if you've got this little chunk of grease, the nonpolar tails of the soap molecules will dissolve or get into the grease. And then on the outside are going to be those polar heads. They're not going to like the grease. And so the polar tails go in there and the nonpolar tails go into the grease and the polar heads stay on the outside. That's two-dimensional. It actually forms a three-dimensional micelle. Well, now we've got this thing here, this micelle, and it's got these polar heads all over the outside. And the water molecules look at that and they're like, oh, you're one of us. We like you. And come on in and we'll just, swim around together. And so now the soap can be taken away in little globules because the soap, did I say the soap can be taken away? I don't know what I said. The grease can be taken away by the soap. I don't know what I'm talking about. We can wash it away because the soap will break it up into little pieces and facilitate its movement away with the water. Any questions? Yes, it's definitely related to some biological processes, lipid bilayers and absorbing fats and different things, yeah. And all of that works because of polar things and nonpolar things.